Okay, in problem number 2 we have a disk. Let's highlight the keywords here. Starts from rest, constant angular acceleration, so there's our angular acceleration, and we know how long it's accelerating, 6 seconds. Okay, it then spins at a constant angular velocity for another 8 seconds, and we want to find how many revolutions. Okay, in this total 14 seconds, so that's the 6 plus the 8. So a couple things this should remind you of right away. We're given two different scenarios, one constant acceleration, one constant velocity, so we're going to need to work this in two parts, and then we are ultimately trying to find the total number of revolutions. So in angular terms, that's related to the theta that we've talked about as far as angular displacement. Alright, so let's see if we can find how many radians this disk has traversed, and we can convert that to revolutions at the end. Alright, so we have an equation for constant acceleration that says theta 2 is equal to theta 1 plus omega 1 t plus 1/2 alpha t squared. We choose this equation because we know the time, we know the acceleration, we know initially starts at rest, and we can decide that our initial reference is 0. So we can solve for theta 2 right here. Okay, so theta 2 is going to be 0 plus 0 times, let's see, we're going for 6 seconds in the first part, plus 1/2, 0.4 radians per second squared times 6 seconds squared. Alright, so that will give us 0.5 times 0.4 times 6 squared. 7.2 radians. Okay. For constant angular velocity, we have theta 2, let's call it theta 3, equals theta 2 plus omega 2t. We'll call that t2 because we're working with a different time period now. And we have no acceleration, so the 1/2 a alpha t squared from our previous equation drops out. Okay, so I'll write that like that. So our final angular displacement is going to be our 7.2 radians. Okay, we don't know omega 2 yet. Okay, we could use a different equation to get here, but let's go ahead and calculate omega 2 based on the information above. Okay, we can find that. We know how long we've gone, we know our acceleration, so we can use omega 2 is equal to omega 1 plus alpha t from the first part of the equation now. Okay, again, this is 0, this is 0.4 radians per second squared, and our time period for the first part was our 6 seconds. Okay, so that's 4 times 6 is 2.4 radians per second. Alright, so that's what we'll use for our omega 2 here. So we take our displacement after the initial acceleration, okay, add to it 2.4 radians per second times our 8 seconds, and that's going to give us a theta 3. Okay, so our previous answer plus 2.4 times 8, 26.4 radians. Okay, that's our total angular displacement. And let's just convert 26.4 radians. We have 1 revolution is 2 pi radians. Okay, so we're just going to divide by, be careful with dividing by this, 2, make sure you get the quantity in there, 4.2 revolutions. Key points to this problem were to identify that it was 2 parts, to work each part separately, and to identify that you needed to do the omega 2 calculation.